So I know you guys plan to collect some traffic data in the afternoon, right? After the lecture sessions today. So I will talk about the traffic detection, traffic sensor, what kind of detector we are using in transportation infrastructure, and what kind of data we produce and how we use those data. And so transportation engineering is a very broad discipline. So we have different topics covered, like surface transportation. So that is the highway related traffic system. We have air transportation, so means the airplane and the freight operation, and we have water transportation, so related the port design and container design and how to design the route for the large ship and carry those containers from place to place. And we also have pipelines. So majorly we use transmit like the oil, like the petroleum and such. So, and what I'm going to talk about is the detection system on surface transportation system. So the detection system, we want to use those detection system, produce the data we want to use. So when we talk about the detection data, we can have different purposes. So we can have real-time operation purposes. We can have long-term planning purposes. So, and I will address those issues briefly using some examples. So we have pretty healthy data detection infrastructure in Hawaii, in Honolulu. So I'm going to show you some website, some system we are working on, and show you the data and how we use those data to generate the performance measurement we want to have, and eventually improve our daily traffic. So, and here is a very typical intersection. So we have the traffic from different approaches. You can see the signal head. It shows the green, red, yellow, allocates the right of way to the different approach based on, ideally, the real-time detection information. So you see the pavement cut. So those are actually, we call it loop, inductance loop sensor. When the vehicle arrive intersections, and the vehicle arrivals actually trigger signals captured by those loop detectors. And loop detector will send the data. So let me show you the details. So those are the loop sensors. And you see the pavement cut. So this is rectangle shape. And sometimes you may see the diamond shape. And sometimes you may see the circle in front of the star bar. So those are the detectors, and detector connect to the controller. This is the roadside controller. So, and the controller has input output facilities, detection card, the controllers, and process all the detection data. And those decisions will be made and sent to the signal head to allocate the right of way, means the green indication to the different approaches. So, but anyway, so and those are the signal head, and signal light we try to use to direct the traffic movements at intersections. We have different control strategies. It could be pre-time signal control. That means we specify the signal timing and according to the time of day, and then we have the signal head green time allocation scheduled based on those pre-specified signal timing plan. And we also can have those traffic responsive based signal control. So that's based on the traffic arrival captured by the traffic sensors, the loop sensors. And this is one example. So tell us, detector just like human beings' eyes. So it detects what's going on, detects how many cars on the road and what's the density of the cars on the road, how many people arrive waiting for the green time to cross the street. And those information detected by the traffic sensor, the detectors, sent to the processor or controller. So like the control cabinet I show you over here. So, and the controller process all the data captured by the sensor, and then have those data for the different purposes and store in the different medias and for the long-term usage, such as transportation planning, or it can be used for the real-time traffic control, like what I show you on this slide. So we adjust the green time for different approach for based on the detection information to better utilize the capacity of the intersections. So, and when we have this framework established, and you can see how important the detection system is. If you do not know what's going on, and basically you may not provide best performance at all. So because its importance, and we have different data collection methods utilized. So the loop sensors, inductance loop sensors, I show you in the first slides, actually is one of the sensors we are using. We have many different types of sensors for different purposes. This is the traffic flow map. We use different sensors collect the data. So we use the Bluetooth device collect the travel time for roadway segment. And then based on the travel time, based on the traffic density, we show the congestion levels. So we use color-coded congestion map to show the congestion, the capacity utilization situation, and deliver those information for the travelers. This is one example, traffic flow, congestion flow map in Honolulu. So, and you can see the different colors represent different congestion levels. Normally green means free flow. So ideally means nobody around you, you can drive and travel as fast as you can. Or the yellow means moderate congestion, and red means heavily congested traffic condition. So, and we have a bunch of performance measurement to define how we can distinguish the situation of free flow, congestion, or stop and go condition. So I'm not going to talk about those concepts, but I want to show you those important information delivered by those congestion map. So, and this is one of the map. I want to show you the.
Yeah, we can see it.
Okay, so, and you see this map. This is a real-time traffic condition map. So you can recognize this is Honolulu. So on the major freeway segment, so like H1, H2, H3, some major arterials, we have the sensors installed and deployed. So, and like I mentioned, we have different type of sensors. I will introduce those sensors, those detectors in the following slides. But we use those sensors to measure the specific data we want. And then we show the travel time, the congestion condition, the density condition with those color-coded congestion flow map. So, and you can see the major route actually is colored by green, yellow, or red section by section. So it shows the congestion level. And you also can see we have some surveillance camera installed from roadway segment to segment. So, and those surveillance camera can deliver real-time image stream to the traffic management center. And you can observe if there's an accident, if there's a congestion, where's the bottleneck. So, and those information is critical for the travelers to select the desirable route we want to use, and for them to choose when we want to leave, so the departure time. So, and this is one example I want to show you how important it is for those advanced traveler information system. So we deliver the real-time traffic congestion information to the travelers. And let me switch back to my presentation. So you can see my PowerPoint file now, right?
Yeah.
Okay, good. So this is a color-coded traffic flow map I just show you. And those are the freeway monitoring system. We use the inductance loop sensor. So loop sensors are different from the loop sensor I show you for the signal control at intersections. Those are we call it dual loop sensors. So we pair up two single loop sensors together and form up a dual loop sensors. Those sensors can measure the ideal traffic data, like traffic speed, like vehicle length, so information, which is critical for the freeway operation. When we have the traffic congestion, for example, we have a crash occurred on freeway, we have a bottleneck form up, and we have congestion transmit backward. So, and we want to know, okay, where's the bottleneck and what's the congestion level, and how we can mitigate congestion using a certain strategies like run meter control, like speed harmonization, like the dynamic routing strategies. So, and when we consider those strategies, we need to know the magnitude of the congestion. So, and we heavily rely on traffic sensor data. This dual loop sensor actually produce the ideal traffic measurement, performance measurement we want, such as vehicle volume, density, speed, and vehicle length. So we want to know how many large truck over there rather than a small passenger car, because the condition, the impact, the congestion generated or induced by those different type of traffic, different type of vehicles are different. So we use the dual loop sensor to measure the traffic condition in real time. And for the arterials, so like I show you in the first slides, we have signal control deployed, and we have different type of control strategies. One of the control strategy we call it actuated signal control. So this is based on the real-time sensor data. And we have the inductance loop sensors deployed, and when the traffic occupied those sensor, and it triggered the inductance change, and eventually the controllers and knows the input from the detectors, and then adjust the signal control, signal timing plan accordingly, and optimize the traffic operation. So this is another applications. We call it run meter control. In Honolulu, in Hawaii, we do not have run meter control deployed because the constraint of our land space, the constraint of our design of the freeway system and local arterial system. So, but this is a quite popular, most effective control mode for freeway congestion mitigation for many states, like Washington, state Washington, like Virginia, like Texas, like California. So many states use the run meter control to reduce the congestion on freeway midstream. The idea is we use the traffic sensor data on freeway, upstream, downstream, on on-ramp, so and on the local arterials, and we detect the congestion level, we detect the traffic demand on ramps, and then we set up the run meter rate. So you can see this is the signal head we installed not at intersection, but at the entrance point of the on-ramp. So, and you can see those signals actually So I got one question from a student. Can traffic detecting technology detect car accident? Yes. So we use sensors to detect the congestion level. When there's an accident occurred, and certainly you will see the traffic density level change. And then we can estimate where's the accident and what's the magnitude of the accident. If you have one lane block or two lane block, or all the roadway segments are blocked. So, and this is a very good question. We do have some methods to detect and estimate the traffic accident. So if you have any questions, feel free to stop me and speak out. So I may not pay attention on the chat box in a timely manner, so I may ignore your questions. But feel free to stop me if you have any questions. So back to the RAM meter control, and we have the signal head installed on the entrance point of the on-ramp. And so we determine how fast vehicle can join the freeway mainstream by allocating green time. What's the proportion of the green time? What's the cycle length? And then vehicle can join the freeway using the green signal, green indication. So, and how to determine the RAM meter rate? This related the detection system, detector data. So we use the sensor data, perform the analysis, and eventually determine the appropriate RAM meter control rate and regulate how fast the traffic can join the freeway mainstream. And this is another example. So you see, this is the intersection. We have a called red light enforcement camera system. So the camera system going to combine with the loop sensor system and form up a red light running enforcement system. So that means if we have a red signal given to approach, when the vehicle run the red signal, so and try to pass through the intersection during the red indication, the capture will, the cameras will be triggered and capture the picture of the vehicles, identify the vehicle. So, and then we can reduce the red light running behavior. So in Honolulu, I know we just have the legislature support to install those red light enforcement camera system in Honolulu. So in the future, when you try to run the red signal, pay attention, there's no camera installed at that intersection particularly. Afterwards, you'll be caught and you need to pay the fine. Before, we do not have such a enforcement camera system. I know Hawaii Department of Transportation going to install at least 6 cameras enforcement system in downtown area in Honolulu. So pay attention, do not get caught if you're around the red signal. But this is a traffic sensor system. So we try to capture the image of the vehicles running the red signal. So, and then we can know, okay, what's your license plate and who owns this vehicle, who run the red signal. And then we can send the bill to the person who run the red signal. So, and this based on the traffic detection system as well. And more importantly, we want to have the traffic sensor system network-wide. So we want to know what's going on in the entire transportation network. So this is an example in Houston. So in Houston, Houston is one of the major metropolitan area in the US. So lots of traffic, lots of transportation needs, mobility demand within this city. So they want to know, okay, what's the congestion level? What's the traffic assignment for those different traffic mobility demand? network-wide. So, and you can see this is the citywide traffic network congestion level map. So we use the sensor to detect the congestion level in the network. And then we can deliver the message recommendations to the travelers and let them know, okay, if you want to travel from, let's say, if you want to travel from point A to point B, so at least you have two options. So, and route 1, route 2, or route 3, or route 4. So, and based on the network congestion level analysis, and you can provide recommendations. So you can have, for example, dynamic message sign shows the congestion level, travel time level for each route, and then let the travelers make decision which route they want to go, and what's the best, what's the fast way they can choose, and eventually optimize the traffic assignment network-wide. So we reduce the travel time for everyone, eventually gets the equilibrium status. And those operation based on the high quality data. So we have to know what's going on, what's the congestion level network-wide. So, and to summarize the scenario I showed you in the previous slides, and basically we need high quality data. So when this data platform provides accurate, timely, complete traffic data, and those data will be sent to the traffic management center. So we call it TMC, traffic management center. And then the traffic management center will use those data to optimize signal control at intersections. So like I show you, we can adjust the signal green indication for each approach based on the real-time traffic arrival data. So if there's no vehicles, we can simply skip the green time allocation for that phase. So, and we can optimize the transit system operation. While the system is quite popular, we call it transit signal priority system. So it's called TSP system, transit signal priority system. The basic idea is based on the detection data, we allocate more green time to the transit vehicles and let the transit vehicles pass through the intersection without stopping. So why we want to allocate more green time to the transit vehicles rather than passenger car? Because from the traffic management perspective, we want to move people rather than move vehicles. So if we can provide high quality travel condition for transit vehicle, that means buses, we can attract more people to use buses. And in order to reduce the vehicle trips, so you move the same amount of people. But if you move them, if you allow them to use the transit bus, and you're going to have maybe one bus carry 50 people. But if those 50 people want to drive themselves, you will have 50 passenger cars, right? So, and you can see when we have those high quality travel condition provided for the transit vehicles, for the buses, we can reduce the vehicle trips and eventually reduce the congestion, right? So reduce the time spent on the road. So that will be a win-win solution. We also want to use the high quality data for the freight operation. So, and we have the trucks, especially those trucks carry the hazardous materials. So we want to know, okay, where's the truck and how we can plan the route for the truck to avoid the community activities. So for example, if there's a parade, and how we can adjust the route for the trucks and to reduce the impact of trucks on the local community. we have to know where's the truck and what's the rear origin destination. So we call it origin destination OD. So origin destination. So and then we can let them know where's the best route we can go. And also we can have those data support for the ATIS, so Advanced Traveler Information System. Advanced Traveler Information System. So basically, we can provide the traffic travel data to the individual travelers, and then the travelers can select the route they want to use and change the departure time and reduce the congestion on the road. So, and those accurate advanced traveler information system actually is desirable for the major downtown area. So because the vehicle density is high, the demand, mobility demand is high. So, and we also can use those data for the dynamic message sign. So we call it e-message sign. So we deliver the real-time information to the traveler. For example, if there's a landslide occurred for a particular freeway segment, and we can have the dynamic message sign show those dynamic information to the travelers, and travelers can take corresponding actions to avoid the roadway segment. And we have also the emergency response system. So if we have the high quality data collect, and we can allocate more green time to the emergency response vehicles and let them to arrive the accident location quickly and to save lives and reduce the congestion, reduce the travel time. So those are the usage of the detection data, and tell us if we have complete, timely, accurate traffic detection data, and we can address most of operation issues. We can also use the data for the planning purposes. So that means we can have the sensor data archive and eventually provide guidance if we want to build up a new freeway segment. Let's say we want to build up H4 in a downtown area. And we need to estimate, okay, what's the traffic demand today? What's the traffic demand 30 years later? And how to address those demands in the morning peak hour, in the afternoon peak hour. And those sensor data provide critical input for us to make the roadway, the freeway segment, not only serve for today's traffic, but also serve for the traffic 30 years later, even 50 years later. So, and when we have different type of data collect, so like I mentioned, for the different purposes, and we need to use different type of sensors. We have a lot of different type of detection sensors. We use those sensors, collect the different type of data. I'm going to introduce some traffic sensor in the following slides. And then I'm going to focus on two type of traffic sensors we are using in today's detection infrastructure. So, and those sensors use different mechanism, like use infrared signal, use sound, so like acoustic sensor, and use the magnetic field change, so use the inductance field change, or combine those technology together. So when we have those sensors deployed, and we have the sensor connect to the detection controller, the controller aggregate those data into a certain intervals. So for example, we can aggregate those data into 20 seconds or 30 seconds or 1 minute or 5 minutes or 15 minutes, depends on the purposes. Different states have different states have different definitions. So those data aggregation intervals is also very important. So like state Washington, they use 20 seconds as a standard data collection interval. California use 30 seconds as a data aggregation intervals. In Honolulu, I see different standards. Most of the cases, we aggregate data in 5 minutes, sometimes in 15 minutes. So high resolution data will provide a lot of detailed information we want to know. So for example, we want to know how the congestion, how the vehicle queue form up, how the vehicle queue dissipate. So, and if we aggregate in 15 minutes, and probably you cannot know those details well, but when you have high resolution data like 20 seconds or 30 seconds, you need a lot of storage media, right? Storage space. So this is a trade-off you have to consider. And when you have the data aggregate into a certain time interval, and you have those data sent to the data server. So, and we use database to manage a large amount of data. So, and then those database provide function for real-time traffic data query. And we also can archive those data for the planning purposes. So this is for the long-term planning purposes, and we can use the data later for the transportation planning purposes. So, and then I'm going to talk about some popular detectors. So, like I mentioned, I'm not sure if you guys know or pay attention on any type of traffic detectors before. Like I show you, traffic inductance loop sensor. This is one of the most commonly used traffic sensor in today's infrastructure. So if you pay attention, you will see the pavement cut at every intersection almost, and on freeway segment. So those are the inductance loop sensor. And also you may see the, the video. So you may see the cameras, right? So at intersections or on freeway segment. So those are the, we call it video image processor. So video image processor, we have the detection algorithm built up within the sensor. And when we have the image captured by the sensor, and the detection algorithm perform and analyze the sensor and detect the vehicles. So I'm going to show you some examples in the next couple of slides, and then I'm going to show you a real system. So, and those are two type of most commonly used traffic sensor. In addition to those traffic sensors, we have many other type of sensors. So like RTMS. So this is a remote traffic microwave sensor. So remote traffic microwave sensor. So basically, install on the roadside. This is the RTMS sensor. So it sends the microwave beam cover a certain area, and those microwave beam will reflect by either the surface or the vehicles back to the sensor. And then the sensor will compare the foreground and background information, identify if there's an object in this detection zone. So we assume on the roadway, so on the detection zone on the roadway, if there's an object, it must be a vehicle. And then we can identify, okay, there's a vehicles. So, and this is the detection mechanism for those remote traffic microwave sensor. Another type of sensor is acoustic traffic sensor. So acoustic traffic sensor is also installed on the roadside. And when the traffic pass through, and the vehicle engine will generate sound. And those engine sound captured by acoustic sensor, and then it knows where's the vehicle and what's the moving speed of the vehicles based on the sound. So acoustic sensor, you can see it won't be impacted by the lighting condition, not like our regular cameras, right? So if regular camera, if this is, for example, nighttime condition, there's no sufficient lighting support, you may not observe the vehicle very well, detect the vehicle very well. But when you use this acoustic traffic sensor, so as far as the engine sound can be generated and the sensor can detect vehicles. So the engine and this acoustic sensor can cover up to 6 lanes in one direction. So it produces a pretty accurate, desirable detection performance for the freeway operation. In the US, we do not use acoustic sensor much, but in Japan, so the Japanese like acoustic sensor very much. So they use the acoustic sensor a lot in Japan. And we also have other type of sensors like infrared sensor. So this is the infrared sensor. Infrared sensor detect object based on the temperature difference. So it's not based on the lighting condition. So as far as the temperature difference between two objects, and this infrared sensor can distinguish those two objects. For example, the pavement surface normally is pretty cold, right? So, and when the vehicle passes through, the vehicle engine is hot. So based on the difference in temperature, infrared camera can detect the objects. So it could be human being, it could be vehicles. So it depends on the application. And we have another type of sensors. This is a magnetic sensor. So magnetic sensor, this is a sensor embedded on the pavement. When the vehicle passes through, on the top of this sensor, it generates magnetic field change. Magnetic field change will be converted into inductance change. Inductance change will be converted to voltage change, and eventually this signal will capture by the roadside unit. So, and you can see this sensor is kind of isolated. There's nowhere connecting this sensor to the roadside unit. So when this sensor is used and it detects the vehicles, send those signals to a roadside unit, and roadside unit connecting with the controller, and the traffic management center can receive those signals. And we also have other type of magnetic sensor. So this is the magnetic sensor underneath the roadway surface. So I have a short video. Actually, I want to show you, introduce this magnetic sensor. So this is a new type of sensor, has pretty desirable performance. So let me show you the video. Can you guys see the video I'm playing? Yes, no?
Yes. Is there supposed to be sound? Can I ask?
Yes. So can you hear it?
We might not be able to.
There's a sound. Can you hear it? No?
No. Yeah. So hold on a minute.
Do you have audio?
Oh, yes. So I think one of the host computers has to share the screen with audio. So Ellen, I don't know if you're there.
Ellen is here.
Okay, so Guohui, if you want to put in the link in the chat window, if it's possible.
Roger, what do you want?
You have to share it.
Is there like is this off the internet? It's not, right?
No, this is the
Okay.
video on my computer.
Okay.
So
So-
it's not available online.
So Alan, if you could just make Guohui like the host, he should be able to share his noise, his sound too. All right.
Should I share
Yeah,
it
start
again?
from the beginning. Yes. Sorry about that.
Okay, so I need to stop sharing and share it again, right?
Yes. And then there should be a little button that says share audio as well somewhere. Yeah, so when you push share screen on the bottom, there's a box that says share sound. You just need to make sure to click that.
Okay.
Yeah, thanks. And while he's doing that, just a reminder to all the students, we saw lots of sensors yesterday on the bike ride, right? So Malia pointed out some of the induction loops where the bike signals, you need to put your foot on a certain spot to trigger it. So just a review of that. Yes, now we hear sound. Yes.
Okay, good.
Construction begins today on the interstate.
We suggest taking the frontage road or alternate routes.
2 of 3 northbound lanes will be closed. Traffic is backed up at least 3 miles.
Look for big delays due to lane closures.
Stop. Now, there's a better vehicle sensing system. Better because there are no poles or overhead structures. There is no cutting, no traffic delays, virtually no maintenance, and it's extremely accurate. It's called the 3M Canoga Non-Invasive Microloop Vehicle Detection System, and it'll improve the way you manage your highways and roadways. The 3M Non-Invasive Microloop System is an intelligent vehicle sensing system for your freeway and advanced detection applications. It allows you to accurately gather valuable data on vehicle speed, count, occupancy, and vehicle length. But what's unique is that the system is non-invasive. You install the microloop probes into 3-inch plastic conduits under your roadways, using standard trenchless or horizontal directional drilling under existing pavement, or open trenching techniques on new roadway construction. It's the same method contractors use to route fiber optic communication cables and other utility lines under roadways. As a result, there's minimal impact on traffic during conduit installation, and your roadways remain intact. The 3M non-invasive microloop system consists of a 1-inch diameter probe, which converts changes in the vertical component of the Earth's magnetic field to changes in inductance. So as vehicles pass, they increase the magnetic field at the sensor, allowing you to gather vital data. The system also includes carriers that hold the non-invasive microloop probes in a fixed vertical position, lead-in and home run cables which are used to connect to the vehicle detector, and the 3M Canoga C800 vehicle detector, which senses changes in inductance from the probe. The non-invasive microloop system offers significant benefits for managing your freeways and roadways. Installing the sensors in a conduit leaves the road surface intact. There's essentially no maintenance because the buried probes aren't affected by environmental factors, pavement deterioration, or other mechanical stresses. And it allows you to keep traffic lanes open during probe installation. In addition, the system is extremely accurate. The unique signal processing algorithm provides count accuracy in all traffic conditions. So the system can resolve closely spaced vehicles and reject adjacent lane vehicles. To install the protective conduit for the non-invasive microloop, use standard horizontal directional drilling techniques. Depth tolerances can easily be maintained by locating the drill head every 4 to 6 feet. Place a 3-inch PVC or seamless poly conduit 18 to 24 inches below the road surface, with the conduit exiting into a handhole. Once the conduit is in position, place the probe in the carrier end piece. Measure the distance between each probe for exact placement. And insert the carriers and probes and lock them in place. You can use single, double, or triple probe assemblies and connect 1 or 2 probe assemblies to the same home run cable. The system also makes it easy to reposition or readjust the placement of the probe to improve vehicle sensing accuracy or to reflect changing traffic characteristics in permanent installations or work zones. Attach the lead-in to the home run cables. Wrapping keeps the conduit free of dirt and debris, yet allows water to move in and out. Route the home run cables to the traffic control cabinet, and then connect them to the 3M Canoga C800 vehicle detector. Then you can verify the installation specification using a laptop computer and program the vehicle detector remotely for optimal performance. The 3M Canoga non-invasive microloop vehicle detection system provides vital traffic information with an accuracy greater than 99% as compared to inductive loops. And the system performs under all road and weather conditions, from -30 to 165 degrees Fahrenheit, and up to 100% relative humidity, including submersion in chemical solutions typical of roadway runoff, which virtually eliminates maintenance, service, and repair. Probes can be removed, adjusted, replaced, and reinserted without disrupting traffic, and the system is placed deeply enough so you can resurface the road without risk of damage. So if you're looking for reliability, accuracy, and greater roadway efficiency from your vehicle sensing system, look to the 3M Canoga non-invasive microloop vehicle detection system.
Okay, so this is about magnetic traffic sensor. So this type sensor provides some advantage, but the installation cost actually is a major factor impeding his wide application. So I do not have any experience deal with this sensor, but it seems it provides pretty desirable detection performance. Another type of sensor I want to introduce to you is actually we call it triple technology sensors. So TT298. This is the sensor look like. So how this sensor look like? So we have three technologies combined into this sensor. So we have radar signal, ultrasonic signal, and infrared signals integrated in this sensor. This sensor can detect almost all the desirable data we want. So including the traffic count, traffic volume, classification, and vehicle profile, its vehicle speed, occupancy, and queue length detection. So it also can indicate if vehicle travel in the wrong way direction or not. So they have three technology integrated, and basically the sensor use infrared signal to count vehicles. So and use the ultrasonic signals to detect the vehicle profile. So including vehicle height, width, and length. And then I use microwave radar detect the vehicle speed. This is the interface of this triple technology sensor. So you can see this sensor installed on the overhead bridge. So when the vehicle passes through the sensor, it can detect the vehicle's profile and including length and height. And then it shows the vehicle speed, the time vehicle passed through the sensor, so the time step, and then estimates the gap between two vehicles. This is called highway in traffic engineering. And measure the vehicle speed and detect vehicle length and measure the gap between vehicles, vehicle highway, and then measure the vehicle occupancy. So actually, when I was a PhD student, I tested this sensor. So it provides very desirable, very ideal data we want. So almost all the data on freeway operations. I also have a very short video. I want to show you how this sensor look like when we have the sensor deployed on the field. So and you can see this is the measurement from the sensor. So it get the vehicle profile, and we care about vehicle length much. So we want to know how long the vehicle it is, and we also want to know the vehicle speed and vehicle length and the gap, the heightway between two vehicles, and then we estimate vehicle occupancy. So this can be converted as a vehicle density. So I talk about vehicle density a lot in the previous slides because we use it as a performance, the only performance measurement to quantify the congestion level. It has different type of vehicles considered, and this sensor can classify vehicles into 11 vehicle categories. So based on the vehicle length, based on the vehicle profile. So it provides a pretty desirable data for different usage. So the major limitation for this sensor is the cost. So for this sensor, the single unit can cost $50,000. So it's pretty costly. So that's about the triple technology sensor TT298. So another type of sensor I want to introduce to you is this sensor. So it has a pretty interesting name, pretty funny name. So it called Turtle. So it's look like a turtle. So, but this is an infrared traffic logger. So we pair those traffic sensor data together on the roadside. So when one of the sensors send out the beam and received by another sensor, when the large truck travel on the road, and you see the traffic axle can be counted when the vehicle cut the beam. So, and the two parallel sensors can tell us how many axles pass through this particular point. And based on certain algorithm, and we will know how many vehicles pass through this designated point. And then we can estimate what's the load of the vehicles and what's the impact on the pavement. So basically, it has wide applications on freeway. So detect instead of the weight emotion sensor. Currently we use a lot, but before we do not have those weight emotion sensor, and we use such a traffic sensor a lot and get the volume of the trucks and volume of the passenger cars in order to optimize the pavement design and pavement maintenance. So this is the type of sensors. We have two types of sensors in the lab. I think you guys, if you pay attention, you can see close to the cabinet, we have two ugly boxes. So those are the turtle sensor. Okay, so and another type of sensor actually is GPS sensor. So GPS sensor has been used in transit vehicles, the buses a lot. And currently we have smartphone, we have in-vehicle navigation system. You guys probably never use like Guohui, those type of GPS sensor. when I was a student, actually, we don't have a smartphone, and if we have we use map when we travel. So I remember I went to Yellowstone Park, so we have really large map planned and the route we want to go. So when we go to an intersection, we have to pay attention, do not miss the important point. And later on, we have those GPS sensor. It's very costly. I think my first GPS sensor cost $300. And today nobody uses it anymore, right? So you have smartphone and you have real-time traffic data, and it's quite convenient. But GPS sensors still be used by those buses. You know, when the bus arrive a bus stop, and it may tell the passengers we arrive University Avenue. So those are the data based on the GPS sensor. So, and GPS sensor can store those information into a locker, and later on you can download those data offline. And today there's many other type of sensors like connected vehicle sensor. So I do not have those sensors included in my slides because those are the advanced technology still under development. So we do not have a theory talking about those connected vehicles. So in the near future, vehicle himself become a sensor. So when the vehicle receive the data they want to use, they also generate data and send the data to the system. So vehicle become a part of the sensor system. And eventually, we allow the vehicle communicate with other vehicles, vehicle communicate with infrastructures. The entire transportation system become an interconnected platform. So, and if in the near future, and we will see lots of information will be transmitted between infrastructure, between the sensors, and so you do not need to distinguish the data from the fixed location sensor or from the mobile sensor. All the data will be integrated and support this interconnected and transportation platform. So, and this is the slides I want to give you kind of a big picture about the different type of sensors and their share in today's infrastructure system. So we have, like I mentioned, loop sensors. So those are the inductance loop sensor, account for about 37%, so almost 40%. We have the video image processor, those type of sensors, so account for 15%. We have other type of sensors like acoustic sensor, infrared sensor, microwave sensor, magnetic sensors. You can see the most commonly used traffic sensors are loop sensors and video sensors. So CCTV is another type of sensor for the different purposes. So we call it calibrated or uncalibrated video sensors. So I'm going to focus on those type of sensors in the following slides. So rudder is 1:50 now. So we want to have a 10 minutes break.
Yeah, we can go ahead and do it now. So
Okay.
Everyone, let us take a 10-minute break for you to get another slice of pizza or use the restroom. And I guess, Guohui, whenever you're ready, everyone should be back by then, and we can continue from there.
Okay.
And I'll go over to the lab right now to talk to the high schools, the Hawaii students, to see if they want to stay in our lab or if they want to go back to H244. So either is fine, actually, from my perspective.
Okay.
So everyone,
Okay.
10-minute break.
Yeah.
Thanks.
So let's continue talking about the sensors at 2.
Yes. Thanks.
Yeah.
Thanks.
So in the following 1 hour, I'm going to talk about the inductance loop detector and video detector. So I probably will spend maybe first 20 minutes and talk about some theoretical calculation behind the sensor. But that's not my emphasis. So I want to show you some system, some algorithm our research group developed and the system we are using today. So I'll give you some examples and let you see how we can use some basic concept or some advanced concept from, for example, machine learning, deep learning, to address the traffic detection issues. So let me talk about some theories we are using in the inductance loop sensor and video sensor, and then I'm going to show you the some applications. I won't talk about or let you use those equations, use formulas, those machine learning approach to develop algorithm yourself, but majorly I want to introduce the concept. Okay, so if you can grab the idea and know what we are doing, if you have issues in the future, you want to address those issues, and you can study yourself or explore more yourself. So like I mentioned, inductance loop sensor is one of the most commonly used traffic sensor. It's the most popular traffic detectors. We can easily find them on freeway, on arterials, at intersections. So when we use those sensors for different purposes, we may have the different design considered. For example, the shape of the detector and how many turns of the wear of the detector and how sensitive we want to have for the detectors. So and those are the issues related, many details. I'm not going to talk much now here, but I want to give you an idea. So what's the major aspects you need to consider when you're talking about those sensors? So basically, this is the architecture how loop sensors work. So we have the control cabinet. So we have the detection card and receive the input signals from the sensors. This is the field components. So we have the inductance loop sensors. We have multiple wears, depends on the sensitivity we want to have. And those sensors and connect to the control cabinet. And this is the picture of the loop sensor. And you can see we have the pavement cut, and we embed those wears into the pavement. So we want the sensors sensitive enough to detect small vehicles, even motorcycle or bicycles. So you cannot put them too deep. So you have to put them on the surface, just embedded them on the surface. And this is the controller. So how the controller look like. So you have detection card and you have power supply system, input output facilities, and you have the controllers. So this is the major computer process all the signals, but it's much more expensive compared to regular computer. So it follows the industry standard. And so when we have the pedestrian or vehicles occupy the sensor on the top of the sensor, and it triggered the signals, trigger the inductance decrease. Actually, it can capture by the detection card, converted as vehicle counts and input to the controller. So some basic mechanism how the inductance loop sensor detect vehicles by the inductance change. So we know from the basic physics, we know when there's a metal, and when we move a metal on the top of the wear, so there's a currency in the wires, it will induce the inductance change. So when the inductance change, this can be measured by the sensor and converted to a voltage change. So and for us, basically what we observe is if we are sensor deployed and when the vehicle approach the sensors, so this is the regular inductance level. When the front bumper of the vehicles arrive the sensor, actually it induced the inductance decrease. So and until vehicle rear bumper pass through the inductance loop, and you see the inductance levels back to its normal level. So because the inductance decrease, we can measure when the front bumper of the vehicles occupy the sensor, when the rear bumpers of the vehicle leave the sensors. So, and we call it time on and time off. So, and based on such interval, if we have, this is the regular output of the inductance loop sensor. And we know when there's no vehicles inductance at a regular high level, when there's a vehicles, we know inductance decrease at this low level. Based on the output like this, and we know there's 3 vehicles because there's 3 inductance decrease, 3 times the inductance decrease. And based on the length of this time on and time off, so we know basically the vehicle length, right? So if vehicle travel at same speed, and we know, for example, this is the output of the sensor when the long vehicle occupied sensor. This could be the output of the sensor when a small passenger car pass through the sensor, right? So because the on time is much shorter for the second vehicle compared to the first vehicle. So vehicle is relatively longer when the first vehicle is relatively longer than the second vehicles based on the on-time difference. So, and this is only one loop sensor, right? So, and based on this sensor output, and we know how many vehicles pass through this sensor. So that is the vehicle count, and we can convert as a vehicle volume. So a single loop sensors can provide volume. And another very important measurement, we call it occupancy. So occupancy is a very, very important performance measurement we use to quantify the traffic performance. So because we cannot, like I mentioned, there's a concept called traffic density. We cannot measure the traffic density directly. So we have to convert occupancy to density indirectly. So, and then shows the congestion level. So, and density can be measured based on single loop output. So density is defined as a percentage of time loop occupied per interval. So if we want to calculate occupancy for this time instant, so we just use Tn1 plus Tn2 plus Tn3 divided by Tn plus 1 minus Tn. So this is the percentage of the loop occupied per interval. So, and there's a problem. Sometimes we want vehicle speed, we want to vehicle length. This cannot be measured by the single loop detector. So we have to convert those measurements to speed to vehicle length. This is more desirable for the traffic management. So in order to do so, we have to pair up 2 single loop sensors together, form up a dual loop sensor. So a dual loop sensors detectors is formed by 2 consecutive single loop sensors and placed several meters apart. So normally this is about 10 feet, 3 meters apart. And dual loop sensor can measure more. So when the vehicle passes through two loop sensors, and based on the time difference and the highway when the vehicle arrive, two sensors. So, and we can measure the vehicle speed. This is more desirable measurement we want. This cannot produce by the single loop sensor. And we also can measure vehicle length. So those are the equations to calculate the vehicle length. And the vehicle length measure can be used to classify vehicle into different categories. So normally Federal Highway Administrations have different definitions in terms of the vehicle classifications. So the simplest way to classify vehicle into two categories, long vehicle or short vehicle. So short vehicle means passenger car, long vehicle means the trucks. So sometimes it could be the 18-wheel trucks. So the reason we want to distinguish the short vehicle and long vehicle, because the impact of those two vehicles on the pavement are quite different. So, you know, the pavement damaged by the vehicles. Here in Honolulu, I think specifically, the pavement need to be resurfacing in every 6 months or 2 years, depends on the location. So, and I do not know if you guys pay the vehicle registration. So if you have a basic, your parents need to pay the vehicle registration. So I have two cars. One is a small car. One is a minivan. So I pay about $300 for a small car as a Civic, and for pay about almost $500 for the minivan, because they collect the registration fee based on the weight of the vehicles. I think that's totally wrong, because compared to the large truck, the damage made by passenger car or by minivan almost the same to the pavement. So if it's a fully loaded 18-wheel truck, it can make the damage equivalent the damage made by 10,000 passenger car. So basically, what your the damage caused by a passenger car can be ignored compared to those fully loaded trucks. But that's give you an idea why we want to know the difference between long vehicle and short vehicles. So we can collect more fees, more reasonable if we know the data, the accurate data about those two type of vehicles. And so this is the overview of the loop sensor input to the controllers. So this is the control cabinet. So like I show you on the first slides, at intersections, if you pay attention, you see this control cabinet. This is the back view of the control cabinet, and you see the input output facilities. When you have the sensor loop sensor data generated, and you input to the input facilities, and then to the detection card, and detection card convert the data into a signal and input to the controller. So and those loop sensors in the field actually the raw data will be aggregated into a certain time interval, 20 seconds or 30 seconds. And those real-time measurements will be stored in the local detection station and sent to the traffic management center. And traffic management centers, they store the data into database, which can be queried later on and for the different purposes. So this is about pretty much the overall architecture of the detection data, collection, storage, and usage. So, and when we aggregate those data into a certain interval, and you can see there's some estimation errors. So you do not output the individual vehicle data triggered by the vehicle himself. So you aggregate them together. Some issues associated with such a data aggregation process, related vehicle sensitivity level, the sensor sensitivity level related the sensor date delay. But from the operation purposes, those 20-second date, 30-second data provide sufficient accuracy we want for most of applications. And you can see the picture taken here shows the single loop sensor and dual loop sensors. So they are used for the different purposes and produce different type of data. And the question here is, we have lots of single loop sensors, but ideally we want to have vehicle speed, vehicle length information, which cannot be measured by the by the single loop sensor. So, and we have to estimate. Some estimation we can conduct is use equation, we call it G-factor equation. And then we use the volume and occupancy data and assume the vehicle length identical, and then we estimate the vehicle speed. After we have the vehicle speed, we can estimate vehicle length. And so I'm not going to talk about the detail, but I want to let you know some data cannot be directly measured. So we have to use the existing data to estimate the data we want. And so there's some estimation errors. So because the assumption we made, any assumption we made, we have to clarify at the beginning. So it shows the application condition of those equations. So eventually we can estimate the speed. The desirable performance measurement cannot be produced by a single loop detector, but based on a certain relationship, and we can get rough estimations. So, and this how the loop sensor data look like. So you have sensor station ID, and you have time stamp, you have volume, and you have occupancy. So also it's called scan count. And then based on the equation we introduce, and we can estimate the vehicle speed based on the equations. We call it G-factor equation. So I'm not going to talk about details, but I want to let you know there's a way we can convert unavailable data from the data produced by the system. That's about loop sensor. So next sensor I want to introduce is video sensor. We have lots of surveillance camera installed everywhere almost. So at intersection, on freeway, like the traffic flow map I show you, you see the snapshot of the signals, right? So of the surveillance cameras. So and we have those sensor data used. So for this video-based traffic sensor, and we can deploy, we call it virtual loop sensor. So, and you can deploy the virtual loop sensor as many as possible and detect the vehicle direction in front of intersections and also can detect the vehicle pass through the intersection in the opposite directions. So after you have the camera produce the image stream, and you have the segmentation or algorithm perform and estimate the parameters and eventually get parameters input to the traffic controllers. I'm going to show you some system I developed while I was a student, and also some more advanced video-based traffic detection system developed by my PhD students and postdoc researchers now. Later after I show you the slides. And so those are the image processors, so video-based traffic sensors. We detect the traffic data directly. And so when we use the video image processor, we want to compare the foreground, background. So we get the multiple image stream, sequential images, and then we get rid of those vehicles and get the high quality background image. And then we compare the background and foreground image, and so the difference must be a vehicle. So, and you can see this is the comparison between background and foreground image. Those objects are vehicles. So, and there's so many challenging issues associated with the video detection. So, for example, shadow impact. So, if I have a strong shadow, the shadow will extend to adjacent land. So, if you have objects like this, it's hard to distinguish that's the vehicle or that's the shadow. So you can easily cause false alarm detection. So we have to identify the edge of the vehicles and remove the shadows as much as possible, and eventually detect the vehicle only. So make the detection accurate. And those are the issues associated with the detection algorithm. Use the background comparison between background and foreground images. Today, we have so many machine learning based detection algorithms. So we train I will show you one examples. We train the machine learning algorithm and recognize where's the vehicle, where's the shadow, and we can get rid of the shadow more efficiently. And this is the one example I developed. So one was a PhD student. So basically, let me show you the program I developed. So this is the program I developed. This is the state Washington state route 520 bridge. So we have the live video input. We also can take the static vehicle, the image stream. There's a virtual loop sensor can be deployed, and it has 3 components. So registration bar, detection bar, and longitudinal bar detect the length of the vehicles. And we have the algorithm developed to increase the robustness of the detection algorithm. So, and you can see when the vehicle passes through those sensors, and you see the registration bar turn from green to purple, and the detection bar turn from blue to yellow. So, and then the vehicle is counted. So, based on the comparison between the vehicle length with this longitudinal line, and we can know this is a passenger car or it's a truck. So, and you can see the camera is vibrate. So because the strong wind, it can still provide a pretty reliable detection result. So, and this is the system actually used by Washington State Department of Transportation to collect the data. This is back to maybe 15 years ago. So, and this is the early detection system we developed. And later on, we have many advanced detection. Let me show you. So, and during that study, we found there's a major problem, the impact from the shadow. So let me go to the example, and then I can interpret the detection algorithm. So, and you can see this is the vehicles, and we have strong sunshine, and the shadow extend to adjacent land. So like I mentioned, if we compare the background and foreground, And we know the objects will be the entire area, vehicle plus shadow. So we can, the computer program cannot tell this is a vehicle or this is a shadow. It can only tell you this is different from the background image. Shadow can extend to adjacent lane and easily cause false alarm detection. So in order to get rid of this shadow impact, so we have to remove the shadow. And before we consider a specific texture, specific color of the shadows, and we can remove it. But sometimes you also remove part of the black cars, so which is similar to the shadow. So what we try to do is we develop a machine learning algorithm. So we use the white vehicle as example, because for the white vehicle, white color vehicles, we can easily distinguish the shadow and the vehicle inside. So, and we use those white vehicle with the shadow as a training data set. And let the machine learning algorithm know where's the vehicle, where's the shadow. And then we apply this algorithm into black vehicles. So, and we remove the shadow of the black vehicles. We need to constantly update our training data set. So basically, I can show you a little bit regarding this algorithm. So you can see this is white vehicle, white car, and this is shadow. Quite different between vehicle and shadows. So and so this is the difference between vehicle and shadows. So we remove the shadow successfully. But for the black vehicles, you can see the vehicle and shadow, they are quite close. So, and if we remove, so if we, so if we remove the shadow only based on the color, based on the texture, and you remove part of the vehicles. And so this is the major problem with the existing algorithm. So what we try to do is use the pattern discovery approach. So we use the white vehicle as an example, remove the shadow and recognize such a pattern and apply to the black vehicles, the dark color vehicles. So, and we can successfully remove the shadow for the dark vehicles. And so use white vehicle as an example. And so you can see the detection result. So this is black vehicle, dark color vehicles, and we remove the shadow successfully. Still, you see some, we cannot completely remove the shadow. So, but it won't impact the detection accuracy. So the purpose for us is to detect the vehicle rather than just 100% completely remove the shadow. So this is one example. We can use a machine learning algorithm and to improve the traffic detection. And today, we have so many advanced detection using other type of sensors, like a UAV-based traffic sensor, drone-based traffic sensor. This is one example produced by my master students. So this is the image stream captured by UAV drone-based traffic sensor. So, and we use machine learning algorithm detect the vehicles. This is the detection drone. And we also can identify the boundary of the roadway, the lane. And then when the vehicle get in this detection area, and we can measure the vehicle trajectory and convert the vehicle trajectory into a measurement we want. So like vehicle speed and vehicle density. So in this area. And this detection condition is quite challenging because drones fly around, so you do not have a fixed background. And background moving, and you have vehicle moving, and drone is moving too. So, and you have to let the program learn and calibrate, and using the training data set, validation data set, and eventually get a good estimation result. So this is the example on freeway. And you can see we produce the vehicle count, number of vehicles, and vehicle speed. So this vehicle speed is not in mile per hour, is feet per second. So that's why you see this is pretty high. And this is one example. This is drone-based traffic detection. Another research we are doing actually is, let me show you. This is a UH campus. So we use the drone-based image processing detect not only vehicle, but also persons. I don't know, let me play it again. So, and you can see, it's not moving, right? It's different players. So you see, we recognize. So those are two students of mine, and they fly drone around. And this, I think, this is the East-West Center. We recognize vehicles and this and recognize person. This garbage being recognized as a vehicle too. So the shape of the garbage being like the vehicles, and those are my two students over here, and it's recognized person and vehicles. And let me show you another video. So this is in the morning. You can see a strong shadow on the road. This is on H1 too. So see the camera moving around, and it can detect vehicles. We convert those vehicle trajectories into a measurement we want. And it produces pretty desirable detection accuracy. So those are the video-based traffic detection. And I want to show you a live system. So we have, can you see my camera system? So let me have one camera start. So we have a project actually on Nimitz Highway, Alabama Boulevard. So include 36 intersections from airport to Waikiki. So we try to install a connected vehicle system. We update all the controller, all the detection system on this Aquiros. So this is one of the, we have all 36 intersections included in this video-based traffic detection system. So, and we have surveillance camera installed. We can get the real-time vehicle image information directly in real time. So you can see, let me choose a standard intersection. Alamano and Wall Street. So you can see we have real-time video images, and also you can see the virtual sensors deployed. It's a little bit slow. So let me save some bandwidth. I'll just show you one camera. Okay, just let me just show you one camera. So we use the wireless communication through the cell phone 4G network. So that's why you see the image resolution is not desirable. So the resolution is pretty low, but it's supposed to be sequential image stream. Let me choose another one. So I don't know what's wrong with the bandwidth. So back to the question in the chat box, how we use the detection technology to detect the accident. Like I mentioned, we can use those sensors to detect the traffic condition change. So basically, if we know travel time become much longer or traffic density or occupancy level exceed a certain threshold, we know there's a bottleneck. So it must be something abnormal occurred. So, and then we can estimate where's the accident, what's the magnitude of the accident. So that's based on the loop sensor, for example. If we have the video sensor like this, basically you can cover a relatively long roadway segment. So if there's an accident occurred, and based on the sensor input, you know the sensor is occupied constantly by some object, and you may know, okay, there's an accident, so there's a bottleneck. Depends on the specific application, depends on the sensor availability. Certain strategy can be developed, certain algorithm can be developed, and eventually identify the accident in real time or near real time. So I think this is more smooth. So you see the vehicle pass through the intersection and the sensor turn on. So and from another approach, so the sensor is on when this rectangle box turn into green, and then the vehicle wait. This is the major street. This is Alabama Boulevard. So it turned to the signal turned to the red, and green signal allocate to the set street. So when the vehicle pass through the set street, sensor turn off, and then controller knows there's no vehicle waiting there anymore, so it switched back to the major street. So you can see it provides a real-time, we call activity signal control strategy. This is the real system, so it's what happened right now. Okay. Any questions about this real video-based traffic detection system? So using those data, let me show you another applications. Using those traffic sensor, the magnetic sensor, the real-time video sensor, and we have this performance measurement platform developed. So basically, you can see those those green dot. It shows the intersections in our study. It shows the performance measurement we want. So basically, it shows the arrival on green. So what's the percentage vehicle arrive on green signal? So it means vehicle will pass through the intersection directly. So there's no need to stop. And what's the pedestrian delay, and what's the control delay for that approach, and what's the transition, and what's the control delay, and also it can identify a specific event. So if there's an accident, specifically we have a subsystem called accident management system. So we use the sensor data to detect accident, and then we convert those accidents into an information which is readable by the system, and we can send the response team to the location quickly. So, and we also can change the signal control plan, signal timing plan for that approach. So, and we can have a lot of advanced performance measurement provided. So for those intersections, we can choose a time of day and then select intersections. Knows the performance measurement, so it shows the signal status too, and it shows the pedestrian call, shows the signal control status, and shows the priority and signal preemption status. Let me show you some historical data. We can measure the vehicle delay, arrival on green, and for a particular intersection, or we can aggregate those intersections together. So we can select, for example, just randomly choose an intersections. So let's choose a station and produced by a certain camera. So 5 and 6, and let's see, eastbound lane 2. Okay, so no data. Let's see if we have control delay data. Okay, bad intersection. So let me choose another one. Sorry. Let me choose as historical data. Nope. So let me see which St. Helens should be the good one. See if this time works. Show delay, flow rate. Okay, I think could be something wrong with the server. I don't know why it won't show the data, but ideally, we should have all the data. Choose a different day. Okay, so sorry, I think it could be something wrong with the server, but ideally I supposed to have traffic flow data and shows the condition, some historical data, but I will double check what's wrong with the server. So later, but that's pretty much is the utilization of the sensor data, how we want to convert those raw data into a knowledge we want to use. So, and you can see the performance measurement not only for the vehicles but also considered for the pedestrians and others. So, and this is pretty powerful data platform. We use it for operation purposes. So sensor data can be used for the operation purposes. Means we are going to use the data to improve the mobility, the operational efficiency. Another example I want to show you is the safety data. So the safety data, we have to collect the data from the police officer's report. So you know when there's a crash occurred, and police officer will arrive and on site and then collect the data. So the police officer collect the data into a report. That report has about 300 more attributes. So, and then we use those data and we develop another application I want to show you. So this is the traffic accident data visualization interpretation study we have. So basically, you can recognize this is Hawaii Honolulu. So we have the safety data collected, and we store those data into a database. And then we can visualize those data. We can perform the online analysis of those data. So, and if I choose area and we want to have all the vehicles in Hawaii and visualize, and let's say if I want to choose Honolulu, all city and towns, and then I want to choose a certain type of crashes. So basically we have fatal crashes, incapacitating, non-incapacitating injury, possible injury, non-injury, or unknown. So, and if I choose all and choose other attributes, and then I can submit request. It will show all the data within this satisfy the filtering criteria. So it shows all the crashes from that certain interval. So from 2012 to 2015. And you can see the crash location, and it also shows the related information. So what's the crash number, who got involved, and what's the driver's demographic information, and so and for a particular location, you see if there's two crashes occurred at same location, and you can see the attributes associated with each crash. And then when you analyze the data, and you also can get the graphic visualization of your analyzed result. So your analysis result. So for example, if I can choose a certain type of visualization chart I want to show, and it shows the related data. So 2012, 13, 14, and 15, what type of crashes it is based on the severity, and what's the relationship between those crash severities with the location of the crashes. And you also can choose another tab. So I think this is quite useful. So you can see the relationship between those data and use those different visualization platform. And you also can generate the graph you want, and and those are the data analysis platform. So, and you can show the data. And more importantly, you can download the data and visualize the data. So we also provide some functions help you to query the data, use the graphic function. So for example, if I want to know the crashes within a specific location, so, and I just have these locations quantified within a Pentagon, so it shows the crashes satisfy this graphic query criteria. And you can perform analysis within this area too. So you can certainly use other shape and perform this graphic query if there's a needs. And that's about the crash, the safety data analysis. So although this is not based on the sensor, but it's based on the police officer's report, and we can analyze the data and get the knowledge we want from the data. So I think that's pretty much what I want to introduce. I'm not sure if you have any questions. I will be happy to answer.